Folks, if any of you, all of you got to the Canvas website.
Oh, the Canvas guys. Oh.
But then I feel like that was for
Everybody's out on the website? Yeah, no, maybe so.
yes.
If you go down to course contents and you scroll down towards the bottom of the page, you should see a file that says ekgs.pdf. And I can't project on the screen tonight for some reason. I can't explain why, but cannot do it. If you go out and you open up that file, you should see several diagrams, the first of which shows an action potential. Are you guys able to see that? If you scroll on down, you should see another diagram which shows the heart, and then it shows off to the right the different action potentials that are being produced at different regions of the heart, like the atrium and the bundle of His and the ventricles. Everybody see that? And then if you scroll on down further to the next panel, you'll see an EKG. You'll see the P wave, the QRS complex. Does everybody see that? So I want you to enlarge that a little bit if you can. Tonight, you're going to record an EKG from a member in your lab group, and you're going to be recording some of these measurements. So if you take a look at the EKG down at the bottom, you should see normal ranges for PR interval. Does everybody see that? So you'll be recording the PR interval, you'll be recording the QRS interval, you'll be recording the QT interval, the ST segment. You'll see it all in the lab. But make reference to this diagram in terms of each of these different waveforms, intervals that you're going to have to measure. Everybody with me on that one? Any confusion about that? All right. And then if you go down to the next panel on the next page, you'll see the representation of a 12-lead EKG. In the top, you'll see the 3 limb leads. In the middle, you'll see the augmented limb leads. And at the bottom of that, you'll see the precordial leads. Does everybody see that? All right, now, here's the question I want to pose to you. If you take a look at that bottom panel, those electrodes are recording the exact same electrical activity. And yet the waveforms are different. Can everybody see that? If you sit there and you take a look, for instance, like a lead 1, and you compare that with what you see in, say, let's just use V1. So if you look at limb lead 1 versus precordial V1, does everybody see it? There's a big difference. It's exact same electrical activity, and yet it looks different. The question is why? Why does it look different? And this comes back to what I had mentioned to you last week. And I was using Eric as kind of an analogy. He said, what I view of him, what I would view of any object, really depends upon where I'm viewing from. So, here's the interesting thing about EKGs and how it is you can be recording exactly the same electrical activity, and yet, depending upon the direction you're looking at, it looks different. So, there's what's known as vector cardiography. you're seeing in those traces is really the representation of vectors. Vectors, vectors, vectors. Mr. Curry, what can you tell me about vectors? They have properties.
They do.
What are they?
I want to say from my memory, the vector, the length of the arrow shows like the quantity of force being produced, and then the direction of the arrow shows
Ah,
full like direction.
okay. Do you have a different answer?
Direction plus magnitude.
Yeah, that's basically what he was saying, is the vectors have got these two properties. They've got direction and magnitude. Over here is kind of the scheme I laid out for you last week. We've got lit lead 1, which is the left arm is positive, the right arm is negative. You're going to need this for tonight. Lead 2, the right arm is negative, the feet are positive. Lead 3, the left arm is negative, the feet are positive. Watch what I'm going to do with these now. Here's going to be lead 1. Lead 1. We're making a number line. And what I'm going to do is I'm going to come along in the center point. I'm going to describe as 0. The first point to the right is plus 1. The second point is plus 2. The third one's plus 3. To the left, negative to 0 is minus 1, minus 2, minus 3. That's lead 1. Actually, if I'd been smart, I would be color coordinated with what I'm showing you over there. But here's lead 2. I've got 0. I've got 1, 2, 3, minus 1, minus 2, minus 3. How do I know that this is positive down here and this is negative up here? Because here's the foot. Here's a positive electrode here, negative electrode here, right? Here's lead 2, positive foot down here, negative electrode in the right arm. Everybody with me on that? If you're confused by that, don't be bashful. Speak up, please. Here's lead 3. vector cardiography. Here's a vector. Here's the electrical activity of the heart. So I'm showing the electrical activity of the heart, and here's what it's doing. If everybody just look at me, here's my heart. And for this brief, instantaneous moment, the electrical activity is doing that. It's going straight down. So in lead 1, what would be the value that we would record in lead 1? Andrew, what would you tell me? Fantastic, that's exactly right. So the way you find out what the value is going to be is, first of all, you have to know, is it moving towards a positive electrode or is it moving towards the negative electrode? And then what you're going to do is you're going to take the arrow and you're going to draw a perpendicular line to a given axis. So this is perpendicular to lead 1, and so by definition, and Andrew, you did a fantastic job on that, the value is 0 in lead 1. So we're talking about the same electrical activity, but we're looking at it from 3 different directions. What do you think? What would the value be for lead 2? Kim, what would you say? For when?
I don't really understand it.
Okay, that's all right. So to get lead 2, I'm going to take this point here, the furthest point of this arrow, and I'm going to drop a line to where it intersects this axis perpendicular. And so you're going to tell me in lead 2 the value is going to be what?
1.
Correct. Everybody with me on that or not? So in lead 2, we would see a value of 1. And what would you say we'd see in lead 3? A guesstimate.
1.
That seems like a reasonable guess to me. He said 1. That seems like a reasonable guess. And I did that to try to get that so that in our EKG, what we would be saying is, if we were looking at lead 1, the amplitude would be neither positive nor negative, it would be 0. And yet, that same electrical activity in both leads 2 and 3 would produce an amplitude of +1. What do you guys think? This is vector cardiography. This is why you can be looking at exactly the same electrical activity, but you're always looking at it from different directions. And so the electrical vector that's being created by the activity of the heart is going to be interpreted differently depending upon where you're looking, the direction from which you're looking. What do you guys think? All right, so here's what you guys are going to do. You're going to work together, and you're going to tell me there's our electrical vector, the direction, magnitude, which the current is moving through the heart, and you guys are going to tell me what type of deflection you'll see in lead 1, lead 2, and lead 3. Give you guys 5 minutes to talk amongst yourselves, see what you can come up with.
1.3.
And I just wanted to lift the rest of it. That's nice. Well, where it starts is where it starts small, so it starts on zero. Yeah, but we're doing like, yeah.
The second time, I think that's when you release the grades, because when I looked at it, I was like, oh, cool. The lowest grade was like 200 out of 215, 225. Like, wow, everyone got an A. And then the updated grade, I was like, oh shit.
Oh, sorry, one. Yeah.
First one, like, what, 6 weeks later? So which one is my second? This one. This one. It's hard to get done. I checked my class now. Oh, I guess it wasn't He said he needs to know.
So then meeting 3 would be possible, meeting 2 would be
What would you guys do?
So we're saying meeting 1 last week.
So lead one. How do you get zero? Are you looking at the rec register?
It's the one on the side. That's what I was like, where you?
I'm assuming that,
Okay, so now, wait, but the swing of it, so would it be negative 2?
Like negative 1.3 is a little bit faster. Or 2 is greater than perpendicular. So it could be a little bit less than light year. So it's not zero.
So you say you're going to, it would be close to zero, is that what you're saying?
What did it zero?
And we're
1.5.
Like the first one. No, because you
That's the time. You look at the point of the arrow, so when you draw something, you look through that point and where it touches each ground. So green and red are exactly like 90 degrees. If the point is a little off of it, it's like just I don't think they're If you look at the black one and you look at the tip of the arrow and follow that to the number line, it's like negative 1.3. It's like where you're drawing that.
so then what would 3 be?
It's just where it's perpendicular to that line.
It's not at all.
Yeah, so you always go from the number line up to that point, and that just makes it's where the arrow hits perpendicular.
Okay, let's see how I do, and since you guys are such tough instructors, you can be highly critical of me. For lead one, a lot of you are saying somewhere around minus 1.5. That's fine. So I'm just going to put here approximately minus 1.5. Lead two. Mr. Vargas, what do you have for lead two today?
We have
Negative 2. Here's what I'm thinking, is that I've got to take this point and draw a perpendicular line to that axis. And there's no way it gets me to minus 2. Maybe. Maybe. That's at maybe minus 0.2, minus 0.3, whatever, however you drew it. What do you think? Is there any confusion on that point?
I guess I'm just getting confused on perpendicular line to draw from.
Yes, we're always drawing a line from the end of our vector so that it intersects a given axis perpendicularly.
How does this example compare? I'm also getting confused too, because like the first one, it was like the dotted lines were like this. So now I'm like,
The dotted line?
like how you drew like the perpendicular line, and there was like the arrow going down, and there was the dotted lines going on the line.
You're gonna have to come over here and show me what you're talking about.
Okay.
Are you talking about the first example?
Yeah.
The dotted line is
So like,
so for that red one,
Would it be in between 1 and 2? Did I actually get it? I got it? Okay. But then, so for
Okay, just to come back, so at least from what I've drawn up here, you may have drawn it a little bit differently on your notepad or paper, it doesn't make any difference. What's critical is you understand the concept. The direction and the magnitude. The direction is it going to be positive, negative? The magnitude we're determining as to where it intersects a given axis at a perpendicular angle. You have a question?
I don't get 2. Isn't the red already perpendicular with the, it's the tip of the arrow, I guess, right?
You don't.
I don't get how you got.
Here's our vector.
Like, isn't it
So
0?
to kind of find out what type of deflection we're going to see in lead 2, we take this very end of the vector and we draw so it intersects any given axis perpendicularly.
Okay.
And so in coming back to lead 2, this the perpendicular intersection is right about there.
Okay.
You guys, you brainiacs agree with me?
Yes. I get what you're talking about,
Green
because
and red
access
are
2
exactly.
is kind of already perpendicular to the brown arrow. So I
Yes, it's close, it's
Green and
close.
red are
Yeah. But the way I've drawn it up there, it definitely is not 0. It's something less than 0. Yeah.
I think what else is if like when you turn your actual drawing so the axes are perpendicular to each other, then you can really tell where
It's because
the
they're
intersector is.
the
You
red
can turn it all you want. But you need to understand that to figure out the direction and magnitude, you have to find out where the perpendicular intersection of the axis. Lead 3, you guys should have found out that for lead 3, it was maybe minus 1.5 or something like that. Positive. So in one lead, we're sitting there saying that we're going to have a very slight positive deflection. In lead 3, we're going to have a negative deflection. And in lead 1, we're going to have a negative deflection. Here's our EKG. And this vector, that vector may represent that point right there in the trace. So these vectors are instantaneous. And all we're doing is we're looking at one specific little snapshot over the course of an EKG. You guys with me on that? So that vector up there represents an instantaneous moment. It's not the entire graph. It's an instantaneous moment within that graph. Yeah, no, maybe so. So coming back, the way you explain that I've got exactly the same electrical event, and yet it's producing entirely different waveforms in different lead systems, is because what we're really looking at are vectors. Okay? That looks like a fun test question to me. She got it all choked up over my explanation. All right, so tonight you're going to be working with the iWork system again. We're going to use the approach that you used when you were recording the EMG of the calf muscle. So you've got your magic little black box. You're going to get what I call the patient cable. Here we go, right here. This is going to go into this connector that's labeled 1, number 1 here. Make sure there's a flat part to this connector. Be very gentle when you put it on in. And then what you're going to do is you're going to take out of your kit, you're going to take the red, the green, and the black leads out. So I'm talking about these little wires that you used last night. We've got alcohol wipes up here. And as I explained last week, what you're going to do is you're going to come along and you're going to take your subject and you're going to simply clean the area on both the left and the right wrists. And then it doesn't make any difference. You're going to take either the left or the right leg, but you're going to take the medial border of the tibia, and that's where you're going to have your third electrode. Everybody with me on that so far? All right, now, you're going to do lead 1. You're going to record lead 1. Here's what you're going to do. Is that the red electrode is going to go here. That's your positive electrode. The black electrode is your negative electrode. That's going to go here. And the ground is going to go here. That's lead 1. Everybody wrote that down, right? Lead 1. Red electrode, left arm, left wrist. Black electrode, the right wrist. The green electrode, that's your ground, that goes on the medial border of the tibia. That's lead 1. Lead 2. Lead 2, what you're going to do is you're going to simply carefully pop off your colored electrodes. You're going to leave the electrodes on the skin. You don't want to lift those up. You want to pop off those electrodes very gently. And what you're going to do is you're going to leave the black electrode here, and you take the red electrode and you're going to put it here. That makes this, the foot, positive. And you're going to put your ground over here on the left wrist. If there's confusion, don't be bashful, speak up. And then to do lead 3, the lead 3, what you're going to do is you're going to leave your red electrode here. You're going to pop off the black electrode, which is here, was here, and you're going to put it over here on the left arm. And then the ground goes to the right arm. That's lead 3. And then you're going to record, I would say, 5 complexes from each lead. And then you're instructed to actually make various measurements of the EKG waveforms. I can't put that up here because I'm not sure what's going on with that projector up there. But that's in the instructions for the lab. Good enough? And what's cool, I'll come back to what I said before, is that EKGs reflect the movement of ions across the membranes of your cardiac myocytes. Because that's what an action potential is, right? An action potential reflects the movement of ions. It's not the action potential that creates the movement of ions, it's the movement of ions that creates the electrical signature. And so the cool thing is that when we look at the electrical signature of the heart, we're actually looking at millions and millions of action potentials occurring all at once. And that reflects the movement of ions. And if your cells are healthy and the membranes are healthy, then the movement of ions is going to be healthy. And the EKG will look normal. On the other hand, if your cardiac myocytes have been damaged, then the movement of ions will be abnormal. And the EKG will look abnormal. You'll learn more about that next week. Okay, so with that, I'm going to set you guys loose. I'll come around and help all of you out as best as I can.
All right, let's do this.
Good.
So then how did he do the other side? It was this way. No, for lead 3.
I don't know.
Yeah. Got it, yeah. And then this would be lead. That's what I see.
It would be, no, so yeah, it would be 1.5. Because this is perpendicular. You want to see perpendicular?
Yeah.
So that's how you know it's 5.
And then this.
For this one, it's because it's not facing 90 degrees.
Guys, let me give you your computers, and then you can go ahead and try to boot those on up.
Yeah.
That's how you got.
I'm plugging into this one.